Another log problem, but done slightly differently here. We have an approximation of log base 5 of 3 is equal to 0.68. I'm okay with 0.7, honestly. 0.7. And over here, I'm slightly okay with 0.4. I mean, if we're rounding, let's be kind to ourselves, shall we? So what we got to do is we got to think of how do we get to a 12 based on 2s and 3s? Well, 12 can be broken down to be a 3 times 4, and 4 can be further broken down to be a 2 times 2. So log base 5 of 12 is the same thing as saying log base 5 of 3 times 2 times 2. If we remember our identities, a logarithm identity says that if you have the product of three things, log base 5 of 3 plus, instead of times, log base 5 of 2, and another log base 5 of 2. Now you can kind of do some shortcut stuff to say 2 squared and have the 2 out in front or whatever. But bottom line is you've got this thing which you now know is approximately 0.7. You have these two guys which you also know are approximately 0.4. So 0.4 plus 0.4 plus 0.7 is 1.5. Same thing can be done here, which is basically just a whole bunch of 2's. Log base 5 of 2, and 32 is to the 5th power. So you put the 5 out in front. Now you've got 5 times the log base 5 of 2. Well, that's, again, we've already got that. We've got 5 times 0.43. I guess if we're just multiplying, it's easy enough to do. 5 times 3 is 5. 15 carry the 1, 21, so 21 with the decimal point right about there. So 2.15. If you had rounded to 0.4 only, it would be a 2.0. So slight variation in rounding errors. And the last one here among these is a 9 and a 4, and I think it's important that we remember that the division type thing means subtraction. So log base 5 of 9 minus log base 5 of 4. Well, 9 and 4 are basically 3 squared and 2 squared, so I've got 2 log base 5 of 3 minus 2 log base 5 of 4. I'm sorry, of 2. So if I have 2 of the 3's, that's 2 times 0.7 minus 2 times 0.4. If I'm rounding and being kind to myself, that's 14, and minus 8 is 6, but with a decimal, it's a 0.6-ish.